Okay, believe it or not, I just totally finished that whole thing and it had stopped recording. But we're going to start thinking about our ring. We know that in order to find the area of this ring right here, right, it's hollow in the center, we need to find the area of the outer circle and subtract out the area of the inner circle. So let's see what we can find out about the outer circle and the inner circle in terms of r and x. So let's come over here and think about what we know. Okay, outer circle. What is the radius of this outer circle? We're in a cylinder, right? The outer circle is just the outer circle, yeah? So it's going to have the same radius as this outer circle. It actually has the same radius as every cross-section in the cylinder before we pulled the cones out of it, right? So the outer section has a radius of r. So this is going to have right here a radius of r. So now we have to figure out what about the little ring, right? So what is this? I'm going to get that kind of out of our way. What about this guy right here? Okay, what is that length? Again, we could think about just giving it another variable name, but what we want to do is figure out what is it in terms of x and r. So let's think about what we can do. And I'm going to do something a little tricky that you probably wouldn't think of on your own, but that's why I'm here, right? Okay, so we know actually a lot about a different triangle that's related to this one. I'm going to go all the way to the top of the cylinder, right? So this is going to be that top base of the cylinder. What do we know about this this bigger triangle right here? Well, we know that from the apex of the cone to the base of the cylinder, this is r, right? Because the whole thing is 2r. Well, what about from the center to this outside portion? Well, that's also r, isn't it? Right? That's the radius of the cylinder. Okay, what's the relationship between this big triangle and this little triangle? Hopefully you can kind of see it. We're looking at the same line. These are both perpendicular to the same line, so they must be parallel to each other. So these angles must be congruent. This angle right here is reflexive. That's in both of these right triangles. So we have some similar triangles here. Let's redraw them over here so we kind of get out of the hecticness of what it looks like over there. And let's see. We've got our small triangle, and all we know about our small triangle is that this is x. We have our big triangle. We know this is r, and we know this is r. This is a right angle, and this is reflexive. The triangles are similar, and what do you know about the big triangle? Well, the big triangle has one side of r and the other side of r. So what kind of triangle is it? It's isosceles. And so if I'm looking at an isosceles triangle, then a triangle that's similar to the isosceles triangle also has to be isosceles, correct? So this actually has to be x. Okay? So using those similar triangles, we can see that this piece has to be x right there. And what that's going to let us do is state that this piece is x. So now, we have our radii for both of these. So what are our areas? So the area here is going to be the area of the big circle, which is pi r squared, minus the area of the small circle, which is pi x squared. And down here, the area is going to be equal to pi times the radius squared. The radius is this whole thing, the square root of r squared minus x squared, squared. Okay, well, what happens when I square something that's been square rooted? Well, I just get the original thing, right? So I get pi times r squared minus x squared. Well, I can either distribute that pi, or I could factor this one out. And what do you see? You see that these two cross-sections have the same area. And what did I tell you about what we could say if we prove that? If we can show that this cross-section has the same area as our circle cross-section up here, and they're both just x away from the center, that x can be any number, so it can be down, it can be up, it can be anything. We've just shown that for every cross-section that matches in height, we have the same area. We have the same cross-sectional area. So Cavalieri's principle tells us that my weird, funky cylinders with the cones pulled out has the same volume as the sphere. So why is this helpful? Well, this shape, the weird one, is made up of a cylinder and cones. And we know how to take the volume of a cylinder, and we know how to take the volume of a cone. And we don't know how to find the volume of a sphere. So now that we can find this volume, once we find the volume of our funky little shape here, then we'll know the volume of the sphere. So how do I find the volume of this? Well, to find the volume, I'm going to want to see where I can write it. I'm too short for that, and this might be a little too low for you. But I know to find the volume of my weird, cylinder with cones pulled out. I keep doing this like I'm doing like the Florida Gator thing, but that's not what I mean. I just want you to remember that the cones are gone. So my weird shape is equal to the volume of the cylinder minus 2 times the volume of one of the cones, right? Because the cones are congruent, I'm pulling out the same cone on either side. Well, what's the volume of the cylinder? Volume of a cylinder in general is the area of the base times the height. Well, what's the area of the base? The area of the base is the area of the circle, which is pi r squared. What's the height of my cylinder? Well, the height is 2r, because I wanted it to have the same height as the sphere, and so I'm going to multiply that by 2r. Minus 2 times volume of the cone. Well, the volume of a cone is 1/3 area of the base times the height. Well, so I have to do 2 times 1/3. What's the area of the base? Well, the base of the cone is the same thing as the base of the cylinder, pi r squared, times the height. And you can see the height of my cone is just r, right? It's not going all the way to the top, it's going halfway, times r. So, we've got, I can kind of simplify this. And just so you know, this is a really advanced kind of idea in geometry. This is a big thing. And even considering cross sections, that's a much more calculus-y thing to be doing. But I think you can handle it, and I think it's cool to figure out, this whole class has been about why things work that you've just been told in the past. So this is an interesting way to attack one of those volume formulas you've been told, and now you can kind of see where that comes from. In one way, where it comes from. It's much easier to do just in calculus. Okay, so I'm going to combine these things. So I'm going to pull my constants to the front, and then I'm going to combine my r's, so I get 2 times pi r cubed. I'm going to do the same thing over here, combine my constants in the front. I get minus 2/3 pi r squared. Yes. And then my pi r cubed. So now I have to subtract these, right? They're like terms because they have the same variables raised to the same exponents. I just need to combine the constants. And 6/3 is the same as 2. And now when I subtract these, 6/3 minus 2/3, jump over here, is going to equal 4/3 pi r cubed. And there is the volume of a sphere. Okay, great job making it through that. I'm very proud of you. You guys have done great work this year. You've learned a lot in a very short amount of time, and I'm very happy you took this journey with me. And let me know if you have any questions before you turn in your final assignment.